turn the volume up in the back? Okay, so is it better now? Okay. Okay. Yeah, so it's about sort of making these technologies a little bit easier to use and develop. And we've heard from some people already in this conference about their experiences sort of as non-experts in differential privacy, sort of coming into the community and trying to use these technologies. And I think some of the themes that came up in those talks sort of motivate some of this work. But just to sort of set the stage, I want to consider a kind of a hypothetical analyst. So imagine there's this analyst who's collected data from, say, a census. And their goal is to produce, say, a two-way marginal between the race of a child in a household and the race of the householder. Okay, and they want to do this under differential privacy. So they say, okay, well, I need to go find a differentially private algorithm for this. So they look through the literature, and they're sort of scanning through the 40,000 plus, I guess, 12 papers. And they come across one paper that compares two algorithms, and they say, okay, well, algorithm A looks pretty promising. Maybe I'll try that for my application. But then as they sort of make their way through the literature a little bit further, they come across another paper, and it sort of appears as though the picture is just the opposite, and that maybe algorithm B is a better choice. Okay? And while this example is hypothetical, these figures are real. So this is actually results from two different papers. So they're not sure which of these techniques to use or whether there's even a third technique that's even better. But nevertheless, they sort of set out and they say, well, I'll just go ahead and try out both of these on my data. Okay? Unfortunately, the source code for these algorithms wasn't available, so they had to implement it themselves. Okay, so they set out to do that. And the first thing that they need to do is they need to think about the sensitivity, because that ends up being a sort of an input to these algorithms, so the sensitivity of the queries or the statistics you want to calculate. So the analyst sort of looks at this table and they say, well, I imagine, if I were to, add or remove, actually this should be a smaller number because that's not a child, so imagine that's, say, 11. So they think about, well, if I were to add or remove a child from this database, well, that could affect sort of one row in this table, and therefore that would affect, the count of one of the cells in this marginal, and it could sort of go up or down by one. So that kind of reasoning is not sort of, that's somewhat reasonable, but it turns out to be the wrong answer for the value of sensitivity for this particular query. Nevertheless, they proceed, and they turn to implementation concerns. So they have to come up with some sort of source of Laplace noise. So they sort of look around and they find some Python package that allows them to sample Laplace variables from some pseudo-random number generator. And so they're kind of working on their deployment. Everything's looking good and they're ready to go. But then they have a friend who knows a differential privacy expert. They say, oh, just before you deploy, watch out for floating point precision attacks. Okay. And so they're like, what? And they point to this paper, and it's very complicated. So they sort of throw up their hands, and they say, oh, I'm just going to use cell suppression. Okay. So hopefully they don't do that. But so this example sort of illustrates some of the challenges that they experience in trying to get differential privacy to kind of work in their application. So they sort of look through the literature. They see conflicting empirical results. There's kind of lack of tools out there and reference implementations for sort of canonical algorithms like the Laplace mechanism. And then there's risk of sort of subtle bugs as they go, right? So, and I think there's bugs at several levels. So there's bugs in the analysis, so doing the sensitivity calculation and making sure that you are reasoning in the correct way about worst case scenarios. But then also challenges in terms of implementation, right? So, I want to be sort of secure against sort of side channel attacks and things like that. Okay. So today I want to tell you about some of my work that tries to make this sort of process easier. So I want to talk a little bit about DP-Bench, which is a benchmark study doing an empirical evaluation of the accuracy of different differentially private algorithms. I want to tell you about Ectolo, which is a framework for kind of doing the kinds of differentially private computation I just described. And then lastly, I want to talk about ongoing work, which is on Private SQL. And this is about sort of an interface that allows you to express, say, a workload of SQL queries that could be complex over multi-relational data, and it gives you back differentially private answers. And so, this is sort of in the spirit of actually trying to eliminate the effort involved for that analyst, and they can just simply, use the system instead, and it will take care of all those concerns. Okay, and the kind of allocation of time is not proportional to these three things, so I'll probably just spend a little bit of time, very little bit of time on DP-Bench, a little bit more on Ectolo, but hopefully have some time at the end for Private SQL. But feel free to sort of stop and ask questions as we go. Okay, so in terms of DP bench, so I think we set out to kind of empirically evaluate the accuracy of various differential private algorithms, and it turns out to be quite complicated because there's many factors that affect the performance, and I won't sort of go through all of them. I'll just highlight one, which is that these algorithms, a lot of them have data-dependent performance because they either sort of adapt to the data, and so or they introduce some other kind of statistical bias when they're doing their differentially private computations on the data. And this is not an exhaustive list by any means, but just some of the examples where some kind of bias is introduced. So we developed DP Bench. There's a companion website, DP Comp, and actually an earlier speaker mentioned this. I just wanted to sort of share sort of one finding, which is that we were able to explain that sort of apparent discrepancy in the previously that I mentioned before about the two algorithms sort of appearing to perform very differently. And basically the idea there is that performance really depends on sort of the signal strength in your data. And that signal strength is governed by the epsilon that you're using, the number of records in the database, as well as other factors. And so if you're in a sort of low signal regime, say really small epsilon or small data, some techniques work comparatively much better than others. But as you move to sort of a high signal strength regime, other techniques tend to dominate. And so that's why so those two papers are really just looking at two very different regimes. Another thing that Ashwin touched on the other day is, we created a bunch of these visualizations. And algorithms had sort of interesting artifacts that you could see visually, sort of rectangular regions showing up in these sort of two-dimensional spaces that kind of puzzled people when they were looking at them. And if you don't know how the algorithm works, it's sort of hard to explain why those artifacts are there. And I know talking to people with the Harvard Privacy Tools project that sort of similar issues arose there as well. But really, I actually just want to say that I think doing this kind of empirical evaluation is really important, and this is sort of more of a call to the community that I think we should be thinking hard about ways to do this and ways to incentivize people in our community to do this. And so, certainly benchmarks is one way, and other research communities really, take their benchmarks very seriously, and it really drives some of the research innovation. Some of the contests, what Christine talked about the other day with what they're doing, I think is a great way of sort of getting people involved. And there's other things like conference reviewing processes where they impose reproducibility requirements that at least gets at this to some extent. So so that's really all I wanted to say about the kind of DP bench work. I want to move on and talk about Ectolo. So this is a kind of a framework for doing differentially private computation. I've already sort of touched on some of the challenges of doing this kind of deployment, and I would say sort of successful deployments have always required a team of experts. You need sort of experts in differential privacy in the room, and it's for a variety of reasons, right? There's limited resources available. There are, I want to say there are really good works like Pink that do some things really well, right? So what Pink does really well is it ensures kind of privacy-safe computation. It'll kind of automatically calculate the sensitivity for you. But it doesn't provide as much guidance on other aspects of the problem. And as I get through Ectolo, I think that should become more clear. And I think in particular, it's very difficult for non-experts to sort of contribute to these deployment efforts because there's just so many ways in which you can kind of make mistakes, right? So there's sort of privacy, it's very difficult to get it right. Even when you want to get highly accurate answers, sometimes need to leverage sophisticated algorithms and maybe do things that are somewhat counterintuitive, thinking really critically about the measurements that you take. And then typically in a deployment, the context really matters. So the sort of particulars of the data that you're working with and variance that may apply, structural zeros, all those sort of things come into play. So it's unlikely we'll just have sort of one black box algorithm we can run, but rather we need a sort of toolkit that allows us to set up a differentially private computation specific to our data. Okay, so that's sort of the goal for Ectolo is to simplify and accelerate this process. It's a sort of operator-based framework, and I'll go into that in more detail in just a second. But the idea is these operators encode some of the best practices in the literature for different aspects of the differentially private workflow. And I put in the sum because, we can't keep up with this field. There's so many great innovations that we have some great ideas embedded in Ectolo, but obviously there's sort of more work to do to continue to incorporate new ideas as they come along. But the idea is that differentially private computation is expressed as what we call a plan in Ectolo. And you can just think of this as it's effectively a sequence of calls to these operators in otherwise arbitrary code. Okay, so I'll actually give you a little example. I'm not going to go, I'll sort of walk you through this slowly, but this is sort of a pseudocode version of the top-down algorithm that Dan Kiefer mentioned on Monday that's being used at the census for the 2020 decennial. It's just to be clear, that algorithm is not implemented in ecto-lo. I think it could be in principle, and really what I want to do is sort of illustrate sort of the kind of potential benefits of thinking in this kind of operator framework by taking that algorithm. Okay. So the way ecto-lo works, right, is you have this plan, okay, and it's executed in sort of a client environment, but there's this API that connects to the database, which is kind of wrapped in this protected kernel, and sort of the only ways you can access the data is through this API, okay? And in that way, we can sort of control exactly how we're interacting with the data. So I'll walk through this code. So the first thing you do is, right, instantiate some protected data source. Let's say it's a table of people. We'll loop over different geographic levels. Okay, so for each geographic level, so state, county, blocked tract, we will select sort of those geographic regions. And then the first thing we do is a transformation operator, where we take that original data set and we sort of split it up into smaller data sets for each region. Okay, we loop over those smaller data sets, and for each one we invoke this vectorize operator, which takes the data from a sort of microdata form into what you can think of as like a histogram over all person types. Okay, so both of these operators here are examples of transformations. They're not actually releasing anything about the data, but simply just manipulating it to prepare it for later computation. The next step is an operation of measurement selection. And so top-down uses HDMM, and that actually is now an operator in ecto-lo. It takes in a workload of queries that you want to answer. Those are represented in a matrix form applied over this vector x. But the only thing that HDMM does is it simply outputs a measurement matrix, M. Okay, so it's actually not touching the private data, but it's just coming up with a good set of measurements to answer the queries in this workload. The next step is to actually carry out those measurements, and so we invoke the Laplace mechanism, but it's embedded in an operator where it takes in this matrix, does the appropriate sensitivity calculation, which may actually depend on earlier transformations that were done on the data. And it gives you back noisy answers. And then the last thing is various sorts of inference and post-processing. Okay, so we want to, at the very least, come up with an x hat, which is an estimate of the original vector that's consistent. But as Dan talked about at length, there's all sorts of other additional post-processing that's being done in this application to incorporate invariance and to ultimately generate microdata, and that's not necessarily captured here. Okay. But one thing I want to sort of point out is if we think about it in this operator framework, there's sort of different types of operators here. Okay, so the red operators, which were transformations, right? This is client code, but these require making a call to that protected kernel to actually transform the data. Okay, and so something has to happen in that trusted environment. But this part doesn't need to be differentially private. We just simply need to make sure that the appropriate transformation is done, and that if it has any impact on later sort of sensitivity calculations, that we record that information somewhere. The only thing that needs to be differentially private is the actual measurement itself, right? Because that's where data is sort of leaving that protected kernel and coming across the line. And then there's all sorts of the green code, which is happening on the client side, which has no impact on privacy, okay? So certainly that includes post-processing stuff that happens sort of after the differentially private computation. But I want to also observe that there's a bunch of things that actually happen before the private computation. And in fact, yes?
I should point to the Laplace measure.
Oh, sorry, no. Imagine that goes up to there. Yeah.
Gold arrow.
Yeah. Yes. Yeah, everything. Oh, yeah. I moved. Everything got shifted down in my last-minute editing. Yeah. Sorry about that. Yes, so this points to the Laplace noise. Okay. But this client-side operation has no impact on privacy, yet it actually is a very significant component of the computation. Like this HDMM algorithm, Ryan, Jerome's student, Ryan, worked very hard and has developed some really nice tools there, and it's fairly complicated, but yet it's all happening before the private computation. Okay. Yeah. So that's the top. Yes, Marco.
maybe I'm sure you're aware of this, but this is the kind of example a bit that, like I think Dave Sands was talking a bit during this week, where it's true that the Laplace, for instance, the gold part is the only one that touched the data, that is really where we have the problem with the data. But in some sense, if you look at the information flow that you have from the data, this is not the only place where the data play a role. Like when you do partition,
Yes.
you do partition on the data. So it's not exactly, I mean, I understand that this is what you are getting to, because the red part, you mean that it should run in a trusted environment because it has access to the data.
Yes.
But I don't understand exactly in which sense you differentiate the control flow, the information flow between the red and the...
I see.
I mean, even in pink, these are differentiated because one is a transformation and one is an aggregation, but there is no real difference in terms of flow of information from my perspective.
Okay, I think I hear what you're saying. I think there is a nice way of decoupling it, and it happens in pink and it also happens in Ectolo, and in fact, we definitely leverage Dave Sands' sort of proof of privacy for pink in thinking about this system. I think the separation is that you do want to, these do need to run in the trusted environment. You want to vet that they are doing the right thing, right? So you could imagine, a transformation that, an adversary could say, well, if Alice is in the data and has this property, I'm going to do this transformation, but otherwise I'll do this one. But really, as long as the transformation sort of is implemented correctly, and you could imagine a non-privacy expert designing a test suite and sort of evaluating that, or writing a proof that, yes, this filter takes in a predicate and applies it correctly. They don't need to know differential privacy expertise. There is a dependence, though, and so these transformations can affect how much noise you need to add here. But I think there's frameworks for handling that, and you can think about basically just the stability of these, the sensitivity of these operations in terms of the symmetric the changes that they make in the data, and then add the appropriate noise.
Think about this more in terms of required expertise than actual flow of...
Yes, I think that's a better, yeah. Yes, Leo.
Somewhat related. So the results of the red operations, are they all like stay behind that API?
Yes. Well, or
what data here, like what is behind the API wall and what one's at the client side?
so there's a few ways of thinking about it. One is you could think of this vectorized operation as actually performing a computation eagerly on the inside the protected kernel. And so now there's like there's an X vector that's in the protected kernel. Okay, I should have clarified. This is just a handle. This actually isn't, you can't inspect this X, right? If you tried to like index into it, you'd get an exception, right? Okay. It's just sort of a handle. The other thing is actually the kernel doesn't have to do anything, right? They could simply just record, and this is the way sort of Spark works as a data analysis platform. It's all lazy computation. It's just saying, okay, I understand you want to perform these transformations, and if you ever actually ask me for the data, I will carry them out. And so this call here could actually invoke a whole sort of, all of the operations needed to prepare the data, then do the measurement, and then the Y actually does sort of, this is actually materialized on the client side. Yeah. Yes, John.
So I think you probably need to say that the programmer has access to the complete schema for the confidential data, right?
Yes.
So vectorize has to make sense.
Yes.
Of that schema and other things.
Yes. Yes, this is the danger of doing a high-level overview with a bunch of experts in the room. I did skip a lot of details, and you've caught them all. Yeah. Okay. Okay. So just sort of concretely in Ectolo, that we have organized the operators into these different classes. I've sort of I think already illustrated what these classes do. Concretely, here are some of the operators we've actually added to it since I created this slide. And I'll just maybe observe things like some of the query selection operators actually are orange because they do actually consume privacy budget, right? So something like what's used in MWEM is to, in a differentially private way, ask which query is sort of the worst approximated one given my current estimate of the data, and you need to consume some privacy budget for that. And leveraging the work by Dave Sands and Hamid Abadi, we have a theorem that says, as long as you vet the kind of red and orange operators, then any plan you write is differentially private. So we took Ectolo, and there's a lot going on in this slide, but we took Ectolo, rewrote a bunch of algorithms as Ectolo plans. And I have these kind of cryptic plan signatures here. You don't really need to digest them all, but I want to highlight some benefits. So one is you see actually the same operator showing up lots of places, right? So LM is the Laplace mechanism, a particular implementation of the Laplace mechanism that takes in a sort of measurement matrix. And it shows up in a lot of different plans. And so if we implement that one operator well and vet it carefully, then it can be applied lots of places. And if we sort of make algorithmic innovations in that operator, lots of different algorithms would inherit that. The other thing is a bunch of algorithms actually have very similar plan signatures, except maybe one operator has been changed. And I think when you look at these papers, I think it's maybe for experts in the room, it's obvious how these algorithms are similar or different, but I think it wasn't until we sort of wrote them down as Ectolo plans that we really saw just how similar they were. And that's an iterative loop, so a repeated process. Yes, Mark?
The exponential mechanism?
We don't have the exponential mechanism as a base operator. Yeah. Yes, there are other operators, sparse vector technique that is not in here. But certainly these are things that we could add.
Just out of curiosity, then how do you implement NWEM?
Yeah, so the worst approximator, if you go to the previous, there's this thing called a worst approximator, that's really a noisy max.
Yeah, this is noisy max behind the scenes, yeah.
So that's it.
Yeah. Okay. Some other benefits, in terms of checking privacy, we really only need to, modulo Marco's earlier comments, we need to vet certain operators, but not all of these operators, because a bunch of them you can see are sort of green, and it doesn't really matter what's happening there. Another thing is kind of with this framework, new algorithms are easy to sort of think up. And so we kind of played around with things like MWEM and came up with different variants of MWEM, just swapping out an operator here or there, and we could actually see significant performance differences by doing that. So it's kind of easy to iteratively develop new algorithms. So that was pretty much all I wanted to say about Ectolo, but I wanted to sort of make a comment about, because I know Salil is talking later about kind of open source tools for differential privacy. And I think our work on Ectolo has got us thinking about sort of, architectures for sort of differentially private systems and what maybe that might look like. And I think there's a lot of benefit of thinking about sort of separate concerns, right? This idea in software design of separation of concerns. And we can see several. I mean, there's the transformations, measurement selection, measurement, post-processing, and then even in post-processing, there's lots of different sort of kinds of post-processing, either sort of getting consistent answers, generating synthetic data, some of the work that Jorg presented yesterday about sort of statistical inference on top of the noisy data. And in general in software, there's obviously benefit of doing this kind of modular design, but in particular in the privacy context, I think there's some specific benefits. One is I think it does reduce the scope of sort of privacy verification. If we're trying to say really be sure that this satisfies differential privacy, there's specific areas where we can focus and we can be very explicit about the dependencies between these operators. The other thing is I think it opens up the opportunity for contributions from a wider community, because I think depending on which task you're taking on, the kind of relevant expertise changes a lot, right? So if you're in post-processing, you actually don't need to know anything about privacy. It's really a statistical problem. Transformations, there's actually a lot of work in the database community on sort of provenance and information flow and in other communities that is separate from privacy, and I think you don't necessarily need to be an expert in privacy to just reason about how one tuple in an input could sort of propagate to changes later on. And of course, the great work by some of the folks who presented on kind of automating proofs of privacy, right, could be very valuable, in certain aspects, certain components of this workflow. Okay.
So, Michael?
Yes.
A question about what's your vision on development of tools using Ectolo? So two related questions, like who do you envision are going to be the programmers or the designers of these algorithms, and what would be, if at all, the role of domain experts, like with respect to this development?
Domain experts in terms of the sort of statistical agencies? Well, I think so. I think you can imagine sort of this entire workflow and thinking about sort of important aspects of the problem. I think, Chris talked about sort of imputation, right, as being an important thing in the community survey. I would sort of view that as an example of a transformation. It's a kind of a complicated transformation, but I guess in terms of sort of who can contribute, we made Ectolo open source. We're continuing to develop on it. We'd be happy to sort of see other people using it and developing it and adding new operators or even adding sort of automated proofs of privacy for different operators. So we'd welcome contributions. Okay. How am I doing on time here?
So about 10 minutes plus question.
Okay. Okay, I guess I'll tell you a little bit about the sort of highlights of Private SQL. So the idea here is that it's a query engine that takes in SQL queries, a workload of SQL queries, and sort of computes differentially private answers automatically. So it is potentially sort of just a useful tool to have, and that's one motivation, but I wanted to highlight sort of two other motivations for the work. So one is that we're seeing in practice like very complicated queries over multi-relational data, and I'll use some census examples to illustrate this. Right, so the census collects data, computes a variety of statistics that can be used for lots of applications. One of the products is summary file 1, which contains both queries about kind of individuals and statistics about individuals, but also statistics about households and people living in the households. When you try to formalize these as SQL queries, I won't expect you to digest all of this, but these queries get quite complicated. This one is actually just a linear query on the household, sort of measuring, counting up the number of households that satisfy certain properties. There are other more complicated queries where this is counting the number of people, but it's counting them in terms of a property of their household, right? So if you think about it, there's a little bit of a subtle dependency between the people you're counting and other members of that same household, and this complicates the kind of sensitivity analysis. And there's even more exotic things where, and this comes up in other applications, but here where it's sort of a count of counts, so we're, for every household size, computing the number of households having that size. Okay. Yes, John.
Where for exotic, if we were demographers, we would say essential.
Okay, okay. So that's one motivation, is these complex queries. I think the other thing is this idea of privacy, not necessarily, differential privacy, not necessarily being a one-size-fits-all definition, but actually needing sort of a variety of different ways of instantiating it. So Ashwin mentioned this before, but I just want to mention that sort of certain data products, you may want to protect individuals, so the number of people, but in other data products, you may want to actually protect entire households. And this sort of shows up in lots of applications. The census I just mentioned. In social networks, people have looked at edge privacy versus node privacy. In event streams, you can think about hiding an individual event versus a window of time versus an entire user's trajectory. And the goal of Private SQL is to automatically generate answers to SQL queries like the ones I show you, given a fixed privacy budget, and then to allow this kind of privacy at multiple resolutions. Let's see. I want to figure out what to cut out here. Well, I'll just say, okay, so really quickly, you can think about sort of two approaches to this. There's been some work on answering SQL queries, the Flex work by Don Song's group and others, as deployed at Uber. One limitation is that this is a sort of query at a time approach, and so the epsilons accumulate, and you get this potentially unbounded privacy loss. Specific to Flex in particular, the semantics actually are a little bit unclear in terms of it hides any row in the database, but depending on the application, this may not actually align. Another approach is to generate synthetic data of various forms, and there's lots of great work on this, but I would say it's limited to data that's in the form of a single table. Okay, so there isn't support for multi-relational data, and in particular, if you were to just sort of generate synthetic versions of each table on its own, if you try to join or link across these tables, you'll end up getting very high error. Okay. So given this background, how do we think about this in Private SQL? We have a solution for this defining privacy at multiple resolutions. I'll just maybe briefly mention it. So we specify a privacy policy. You pick one table as your primary private object, but then you think about neighboring databases as adding or removing a row from that table, but also actually all of the tables that kind of transitively refer to that table. And so if we were to take, say, this data here, let's look at household privacy. The household is the primary private relation, but neighboring databases occur by adding or removing not only a row in the household, but actually all of the members of that household as well. Okay. And while this is, a kind of a very reasonable sort of definition, the point is to automate this and allow us to choose the policy that we want and have the system kind of automatically do the appropriate sensitivity calculation. Okay, so I'll just walk through the sort of overview of how Private SQL works. So the key is, the first step is this idea of view selection, and this is one of the main ideas, so hopefully I can get through this. So what is a view? So a view is a single table that is the result of potentially a complex query over the original input tables. Okay. And in particular, we want to select views so that every query that the analyst wants to answer can be computed on just one view, and in particular, that computation is linear over the view. So you can think of it as basically a counting query over where you specify a predicate. It's a little bit more general than that, but that's the basic idea. So you could imagine here could be a view, right, where you have each row corresponds to a person, but notice that we also are encoding the household size, right, which is actually aggregating information about multiple people and recording it and attaching it with each person's record. The next thing we do is we take these views and we generate differentially private synopses. And so we can leverage all the great work on sort of taking a table and generating a differentially private version of it. This could be synthetic data, this could be histograms, or tabulations, whatever is appropriate for the application. We have to allocate budget across these things. I won't get into that. And then we need to ultimately answer queries. So you now imagine that an analyst writes a complicated SQL query over this data. We have to rewrite it in terms of these synopses. This is a well-studied problem in the database literature of sort of query answering over views, and so we can leverage the work there. But the analyst can do this sort of all day long because it's just post-processing on these produced views. One of the most interesting things is the sensitivity calculator, which is thinking about, and this has sort of already come up a fair bit in the talk already, thinking about how a change to the original source data could propagate and be a change to these views. Okay. And so this is a very complicated problem. I want to just highlight sort of a few aspects of it. So doing this kind of sensitivity evaluation is hard, and Marco actually has a nice paper sort of proving some hardness results there. We leverage some work in Pink and Flex to have this kind of sensitivity calculator that produces an upper bound on the sensitivity. We have some kind of new ideas there that actually have a very significant impact on the accuracy. But even if we sort of have this calculator, unfortunately the sensitivity in some cases can be very high or even unbounded. So if you think about this example, right, where I've encoded this household size, the worst case database is everybody lives in the same household. If I were to remove one person from the data, every row in this table would then change, right? So how do we get around that? I mean, this is not a uncommon thing, but we have this idea of using truncation where we sort of try to estimate the general frequency of, say, household size, and then cut things off and impose these kind of truncation operators into the view to bound the sensitivity. There's definitely other techniques out there, but that seems to work well for our application. The last thing, which I think is really interesting, is thinking about this supporting multiple privacy levels, so household, person, and so on. What we do is we have a view. So what we want to do is have this thing not have to be rewritten every time we change the policy. We'd like this to be sort of general, but then we want to be able to change the policy and have everything work out. And so what we do is we have this view rewriting step where we actually make the dependency on the kind of primary private table explicit. So I'm skipping over the details, but you could imagine you could have a query that's just about people, about the person table. But if the household is the primary private object, then actually we need to think about those changes, and we can actually add sort of joins or semi-joins with the household table into the query plan, and then that actually makes that dependence explicit. Okay. So we rewrite the views, and we can support acyclic dependencies, cyclic dependencies. So imagine like a table that encodes a family tree. So-and-so is the parent of someone else. That's more complicated. I'll skip over the empirical evaluation. We compare with competing techniques. Okay. We compared with Flex, and this line here is actually just reporting 0, so we want to be below that line. It kind of depends on the size of the query answer and things like that, but we can, in the sort of improvement comes from several things: the sort of tighter sensitivity calculation, doing truncation instead of smoothing. So smooth sensitivity is an alternative. Truncation, at least in the applications we looked at, seems to actually give us much better performance. And then we have this kind of better composition because we're using these views, and then we can actually leverage parallel composition across queries to the same view. So just to wrap up with Private SQL, so I think this idea of view selection and synopsis generation is an interesting approach and gets us away from some of the thornier issues of just answering one query at a time. We can support privacy resolution at multiple levels, and we can sort of do it in an automated way, which I think is really nice. But there's lots of hard problems here in terms of bounding the sensitivity. There's lots of, and just in terms of that, there's lots of open questions with all of this, with this project. But in particular, with the kind of sensitivity calculations, there's some really nice work on sort of more sophisticated mechanisms that we could potentially use here. I think there's some really interesting questions around this bias variance trade-off. So if I do truncation, I'm injecting some bias, but it substantially reduces the amount of noise I have to add. But what is the right sort of threshold to pick? How do I pick that threshold in a differentially private way, and so on? And then, of course, Emma, and this has shown up in other conversations and talks, if I am injecting this bias, how do I quantify that error and let the end users actually understand the impact of that? Okay, so just to wrap up, so we talked a little bit about benchmarks and their potential value to the community. Ectolo is sort of a tool for simplifying and accelerating this kind of algorithm development. And then the work on Private SQL, we're excited about that, and it opens up this possibility of a kind of declarative interface, so a user doesn't need to know about privacy, they just sort of express the queries that they want to answer, and the system can do it for them and support kind of queries over complex multi-relational data. Okay, so that's all I want to say. Thank you.
So I have a programming language background, so I was wondering when you implemented Ectelo, which programming language you use, and if that helped you out, to do the implementation easier, to facilitate the non-specialists to not make mistakes. If you can give me a little bit of experience on that. So
we chose Python, maybe for more practical reasons. I think just to be clear, we have these operators that actually do the sort of differentially private computation. Sort of for Ectolo, we can kind of treat those as black boxes, and sort of we set aside the problem of actually carefully vetting that code to make sure it's differentially private as sort of a separate problem. So, but you could imagine, in a sort of production system that maybe you'd want to replace that with a language that's more amenable to analysis and where you'd actually write sort of an automated proof. But since so many people are already actively working in that space, we decided to leave that problem to them. Yeah, good question.
I actually have a question. When you were, can you elaborate a little more on the choice of dropping outliers? So what do you do exactly?
So we, with the view rewriting. Yeah. So we, so for instance, say with the house, like a query about people, but the private object is the household, we would estimate, so we use some differential privacy loss budget to estimate sort of household sizes. And we can do this in a general way where we sort of look over the base relations and look at sort of the frequency we look at attributes that occur in the queries, and then we look at the frequency of those attribute values in the base tables on the data in a differentially private way. So now we get a distribution for sort of how frequently each value occurs. And then we can choose a sort of cutoff point, right? So in this case, like concretely, like large households would just get sort of dropped from the data. And then we can actually, we write that truncation operator explicitly into the view. And so now our sensitivity calculator can reason about that and say, well, I know that because of this truncation operator, now I can bound the sensitivity.
The size of the range is smaller, mainly. Yeah. I mean, you can fix the range.
Exactly, yeah. And smooth sensitivity, I think one problem there is that there is this sort of long tail, and so the smooth sensitivity is going to sort of look at the max, right, and then come up with a smooth upper bound on it. And so not only is it sort of starting with a larger value, but then actually because you're doing this kind of recursive calculation on the view, that starting with a larger value sort of compounds because later operations could sort of double or, have a doubling effect on that.
John,
Just a quick follow-up too. So you just said you remove those past the
Yes.
threshold. It's not that you put them sort of at the threshold value. They're just gone.
We drop them. I think in part there's some work by Dave Sands that looks at, there's some subtleties with sort of how to drop them partially. So because if you just sort of take if you have a deterministic algorithm that just sort of takes the top ones, then there's subtle things where if you, yes. So we just drop them, but I think you could potentially do, smarter things, and that's something that we're looking into.
So this isn't a question, it's a comment and kind of a suggestion. I've known members of this team for more than a decade, and they've been working on hard problems like this for at least that long. A lot of the recent progress, to be frank, has been motivated by having a pretty well-defined use case, which is the massive amount of publication that the Census Bureau does from the decennial census. This team, for example, is the first one to systematically go through the publications and try to express them in a standardized database language so that it opens up the tools that you could use from that language. It's really shed a lot of light on what we do that can be addressed by specialties that are largely absent from the Census Bureau. When the demographers at the Census Bureau think about this problem, they have a table writing language that they think about it in, and that table writing language is the progression of generations of software designed to operate on hierarchical databases that were household surveys. Some people, many decades ago, tried to restate all that in terms of relational databases, and basically the user community pushed back, and it went back to the format that they were used to using. Now we have a really good use case for not just differential privacy, but for rethinking the way that the entire workload is conceptualized. What does this table really represent in terms of the underlying data? It's really enormous progress all below the surface, so it doesn't necessarily produce something usable, but it came from being motivated by a really specific use case. I think that's right, isn't it?
Yeah, oh, absolutely, yeah.
And basically, it's also a call for more benchmarks, right? Like the more rich benchmarks we have, the more of these problems will surface, and we will be solving kind of problems that are more realistic.
I think we all realize that, and we are on the same page. Very quick.
So, I'm guessing from the citations you put at the end, but you haven't used the phrase like restricted sensitivity when talking about this truncation operation. Can it be understood in that framework?
Yeah, I think so. I mean, I think
Like
it's,
Lipschitz transformations?
yes.
Yeah, so,
Yeah.
so basically, I don't know, yeah.
Well, I think it's maybe like a simple version of that. I think that is a really interesting direction to think about in terms of sort of coming up with more sophisticated.
Yeah, people have looked at answering a single query using Lipschitz transformation. Here we're trying to answer a set of linear queries in the same view, and so how do you, like the other citation that the recursive mechanism, we are figuring out ways in which you can use this where you can do something in the recursive mechanism but answer multiple linear queries on it. how do you do that with restriction sensitivity or Lipschitz extension is an open question.
Well, the recursive mechanism is a Lipschitz
But it's
extension.
a nicer, it's a slightly nicer, we'll talk about it offline.
Yeah, I think taking this offline is better. But let's thank my colleague.